Welcome back, everybody. This set of notes is going to be for your 4.3 fill-in-the-blank notes, and we're going to cover how to determine the number of protons, neutrons, and electrons. That should all be a review for us. But then we're also going to delve into the topic of what isotopes are and how to calculate average atomic mass, as well as get a quick preview of the periodic table. So as I always like to do, let's go ahead and look at the objectives for today. So we're going to talk about what makes elements and isotopes different from each other. We're going to calculate the number of neutrons in an atom, calculate the atomic mass of an element, and explain why chemists use the periodic table. So the first one that we're going to discuss is the atomic number. And here it says atoms are composed of identical protons, neutrons, and electrons. So it doesn't matter what atom it is. If there's a proton in one element, it's going to be the exact same type of proton in another element. It says, then how are elements of one element different from one another? So if I have an atom A and I have atom B, what makes them different? What makes them two different elements? And elements are different because they contain a different number of protons. So I might classify element A having 3 protons, and element B, the classification for that might be 4 protons. So this atomic number of an element is also the number of protons in the nucleus. So we discussed this formula in class that the number of protons in an atom equals the number of electrons as well. So the atomic number is equal to the number of protons, and this number of protons can also tell us the number of electrons in a neutral atom. So sometimes chemists like to make abbreviations, or like if we don't know the atomic number, we'll just use this letter Z. So we'd say the atomic number of an element, Z, is the number of protons in the nucleus of each of the element. And we did a little chart earlier in class, but remember, if we look at the element carbon, its atomic number is 6, and then therefore we know that it has 6 protons. Same thing we see with phosphorus. The atomic number is 15, so therefore we know it has 15 protons. Finally, gold, atomic number 79, number of protons 79. So there's a direct relationship between the atomic number and the number of protons, and that's important that you memorize that relationship because you will be making these calculations on the test. Now the next number that I want to discuss is the mass number, and we have also worked a little bit with the mass number, but here's a review. So the mass number is the number of protons and neutrons in the nucleus of an isotope or an atom, and we had seen this formula before where we can take the mass number and it equals the number of protons plus the number of neutrons. And so when we have different nuclei, okay, when that's just talking about the nucleuses of different elements, if we find the mass number is 18, we know that oxygen's atomic number is 8. We can therefore find the number of neutrons and electrons. And the way that we would go about that is, remember just on the last slide we said that the number of protons is equal to the number of electrons, so 8 and 8. And then, in this case, to find oxygens, we will take the mass number 18 here, and you can see it's already over here for us. We will subtract the number of protons, which is 8, and this gives us a number of 10. Because remember, the mass number is equal to the number of protons plus neutrons, so if I want to find the number of neutrons, I'm just going to take the mass number minus the number of protons, hope you can read my writing here, equals the number of neutrons. So let's look at arsenic. Arsenic has an atomic number of 75, and it has a atomic number of 33, and so we can say that there's 33 electrons and then 42 neutrons. So again, if I was to go 75 minus 33, this gives us a number of 42, and that's our number of neutrons here. Go ahead and just look over phosphorus for yourself here. So sometimes I'm going to ask you to write the symbol for a specific element, and when we talk about writing the complete symbol, so pay attention to this word here, the complete symbol of an element includes the mass number and the atomic number. So for example, here's our symbol X. I'd want to include the mass number at the bottom and the atomic number at the bottom, and the mass number at the top. So let me give you an example. So if I have carbon carbon contains 6 protons, its atomic number is 6, and its mass number is 12. So that would be the complete symbol for carbon. On the other hand, oxygen has an atomic number of 8, and it has an atomic mass or atomic weight of 15.99, but remember we round that to 16. So this would be the symbol for oxygen, and this would be the symbol for carbon. So here's an example where we might give you a symbol and ask you to calculate these. So this one says find the number of protons, neutrons, electrons, atomic number, and mass number. So I'm going to start with the bottom of this list because I think this will be easier. So remember the atomic number equals the number of protons, and the mass number equals the number of protons plus the number of neutrons. So just on the last slide we said that one of these numbers had to be the mass number and one had to be the atomic number. So if the atomic number is only including the number of protons, it's going to be a smaller number than the mass number. So I'm going to say that this is the atomic number. So I'm going to say 35. And then the mass number, this one's bigger, I'm going to say is 80. So let's start back at the top again. The number of protons. Well, remember we said the number of protons was equal to the atomic number, so I'm going to say this has 35 protons. Then the number of neutrons, remember making this calculation was a little trickier, so I'm going to make this calculation off to the side here. I'm going to take the atomic mass, or the atomic mass number, take this number 80. I'm going to subtract the atomic number, and this is going to give me 45. I hope my math is working out well. So I'm going to say 45 neutrons, and then the number of electrons, remember, is equal to the number of protons, so I'm going to say is 35 here. So here's a slide that is another example problem. So go ahead, pause the slide, write down your answers, and then unpause it, and you'll see the answers in just a second. And here we go. It has 34 protons, 44 neutrons, and 34 electrons. Remember we said these two numbers are generally the same. And the complete symbol for this would be selenium with an atomic mass of 78 and an atomic number of 34. Here we go. Here's our final answer. Here's another problem. This one is a little bit trickier. Notice that they're giving you 91 protons and 140 neutrons. So go ahead and calculate the atomic number, mass number, number of electrons, and give me the complete symbol, please. Go ahead and pause the video, and I'll come right back with the answer. And here we go. The atomic number is going to be 91, since there is 91 protons. Remember, those two numbers are the same. The mass number, I took the number of protons plus the number of neutrons to calculate this mass number. Then the number of electrons is the same as the number of protons, so notice those two numbers are the same again. And the complete symbol here is Pa. I just looked up 91 on the periodic table. Remember, we put the atomic number on the bottom, the mass number on the top, and here is our complete symbol. Here's another example, so go ahead, pause the video, work through it, come back and match up your answer. So for this one, it said that there were 78 electrons. Remember we said that the number of electrons is generally the same as the number of protons when we're working with a neutral atom. So the way that I did this was the atomic number was 78 then. To find the mass number, I took the number of protons and the number of neutrons, and it came up to 195. Number of protons, of course, was 78. And so here's our complete symbol, and it happens to be platinum with its atomic number of 78 on the bottom and its atomic mass of 195 on the top. So the most important topic that we're going to talk about in this video that is new is this idea of isotopes. So another thing that Dalton had a little wrong in his theory was that all elements were identical to each other. So atoms of the same element can have different number of neutrons. Remember the thing that we said that makes an atom a specific element is the number of protons, but atoms can have different numbers of neutrons, and we'll soon find out electrons as well. But the thing that makes an isotope is having a different number of neutrons. So thus, it's going to have a different mass number, because remember, our mass number was equal to the number of protons plus the number of neutrons. And so if I change this number, I'm going to end up changing my mass number. So these things are called isotopes. So isotopes are atoms that have a different number of neutrons than, I'm going to say, like your typical atom does. So isotopes were first discussed or proposed by Frederick Soddy. You can see his lifespan there in 1912. Isotopes are atoms of the same element having different masses due to varying numbers of neutrons. And Soddy won the Nobel Prize for Chemistry, so this is obviously like an important topic or concept that he discussed and that we're now learning about. Isotopes are also really important because they deal with this idea of radioactive materials. So how do we name an isotope? Like, how do we identify that an atom is in fact an isotope of an element? Well, we put the mass number after the name. So normally we would say that our regular carbon-12, okay, so remember carbon-12 has got 6 protons plus 6 neutrons, and this is the mass number, so we'd say 12 equals 6 protons plus 6 neutrons here. And then we have carbon-14, so 14, we know if it's going to be an atom of carbon, it's going to have to remain with 6 protons. But how many neutrons are we going to have here? Well, I'm hoping you're saying, oh, we're going to have 8 neutrons here. So notice that both of these are still carbon because they both still have 6 protons, but they're considered isotopes of each other because they have different numbers of neutrons. Now let's go ahead and look at uranium-235. We normally would see uranium with a 238 after it. So this is its typical, kind of like carbon-12s are typical carbon, but you can tell that this is an isotope. So sometimes the number of neutrons might be less than what the original or the main type normally has. Now here's a great classic example of our 3 different hydrogen isotopes. So again, we have the definition at the top. Isotopes are atoms of the same element having different masses due to varying numbers of neutrons. So we can see the 3 hydrogen isotopes. The first one's called protium, then deuterium, then tritium. And one thing, I know these words look confusing, but if you just look at them, look at the prefixes, pro generally means 1, dew means 2, and tri means 3. So there's some clues there about what's happening. So let's look at the mass here. Mass is 1, mass is 2, mass is 3 for tritium. So when we look at the chart, notice that they all have the same number of protons. And this is important because they all are the same type of element. They do have the same number of electrons, which is good. But now notice each one has a different number of neutrons. So if we were to look at the nucleus of a hydrogen-1 or a protium atom, what we would see is there's just one positively charged particle there. One proton. You might be, well, what's up with the electrons here? Well, remember the electrons live in the electron cloud outside of the nucleus. And then, of course, since there's no neutrons, there's no other subatomic particle there. But if we look at hydrogen or deuterium, we can see that it's going to have, I'm hoping you're seeing this, it has 1 proton and 1 neutron. So here's our 1 positive charge in the yellow and our 1 neutrally charged particle in the orange. Then tritium here is going to have 1 proton and 2 neutrons. So again, we have our 1 positively charged particle in the nucleus and then our 2 neutrally charged, our neutrons, also there. So here's an example again of 3 different isotopes of the same element, and notice that each element, we know it's an isotope because they have a different mass number. So when scientists study elements as they occur in nature, they find that there's not just one type of atom or one atom with just a single type of mass, that they do occur with these different isotopes. So we just reviewed this. Hydrogen occurs in nature with 3 different isotopes. Here's our protium, our deuterium, and our tritium isotope. When we look at helium, as it occurs in nature, it appears in 2 different isotopes. Again, remember that there's 2 protons here, so do you see the 2 pink particles? The only thing that's changing is the number of neutrons. Same thing for lithium. Lithium also has 2 naturally occurring isotopes. Again, notice that there's these 3 pink for each of them. The only thing that's different are the number of neutrons. So this one has 3 neutrons, this one has 4, and also look at the mass number. I just kind of crossed it off for lithium there, but it was 7 a second ago, and that's because there's 7 particles in the nucleus. This is lithium-6 because there's 6 particles in the nucleus. So it says here, isotopes are atoms of the same element that differ in their number of neutrons or have a different mass number. Now let's go ahead and talk about the atomic mass. So how heavy is an atom of oxygen? And really that depends because there's different kinds of oxygen atoms. So the idea is if I was to ask you how heavy is a lithium atom, remember from the last slide, you'd say, well, it depends. Is there 3 neutrons or is there 4 neutrons? So oxygen can also have different isotopes. So when we talk about the average atomic mass, we are more concerned with the average atomic mass. And so you'll sometimes hear me use those words atomic mass, average atomic mass interchangeably. And this average atomic mass, this is what we actually see on the periodic table. This is the thing that's in the decimal form. Remember I told you that's how you could figure out which one was which. And this average atomic mass is based on the abundance, or percentage is another way to think of it, of the variety of each element as it appears in nature. So we don't use grams for this mass because the numbers would be too small. So remember we use AMUs when we're discussing this.